So we'll move forward with Dr. Qinglan Ling, who is an assistant professor at UMass Chan Medical School, and they will be talking about developing gene therapies for mitochondrial diseases. So I'll turn it over to you, Dr. Ling.
Let's see. Can you see my slides?
Yes, but they're not in presenter mode.
Okay. How about this?
Oh, perfect.
All
Thank
right.
you.
Awesome. Thank you, Jessica, for the nice introduction. And thank you, Mito, to give me this opportunity to present my work. And like I just started my lab as an assistant professor here at Gene Therapy Center at UMass Chan Medical School about 2 months ago. And before that, I was a postdoc at UT Southwestern with Dr. Stephen Gray in Dallas, Texas. So for the last 6 years at Dr. Stephen Gray's lab, we were working on developing gene therapy for SIRF1 syndrome. And that's how I met Casey and the rest of the SIRF1 and Leigh syndrome community. So today I'm going to give a very broad overview of the work that we've done in the last 6 years on gene therapy for SIRF1 Leigh syndrome, as well as the continuing effort to develop gene therapy and in a more efficient way, and hopefully we'll get to a cheaper way for different mitochondrial diseases with a focus on Leigh syndrome. So I'm going to start from the basics. The mitochondria has a very important function, as we all know, is to produce ATP. So under anaerobic conditions, the glucose is metabolized into pyruvate, which then is converted, going through the oxidative phosphorylation process and produce more ATP from mitochondria. However, under anaerobic conditions, the pyruvate is converted to lactate, which limit the amount of ATP production. Therefore, with the amount of ATP that produced, this is not only important for the for ATP production, but also for many other functions, such as biosynthesis and gene expression, catabolic switch, cell fate and function, and many other functions. So with all those important functions from mitochondria, as we all know that any mitochondrial diseases, they are multisystemic, which can cause neurological symptoms as well as non-neurological symptoms. And for patients, even with the same gene or mutations, we can see symptoms that cause dysfunctions in different cell type or organ systems. With all that information in mind, we think adeno-associated virus can be a great gene delivery vector due to its high safety profile. Currently, there are over 300 clinical trials initiated using adeno-associated virus, or AAV. And AAV is non-pathogenic. It is efficient in delivering genes to dividing and non-dividing cells, which means that it can be very efficiently to treat dysfunction of neurons. And AAV can be natural occurring serotypes, or can be engineered to different types of capsid to deliver genes to different organs. So currently in the clinical trials, most often are used AAV serotype 9 or AAV9, and many researchers in the gene therapy field are actively looking for the new natural occurring AAV serotypes or engineer them so that we can target specific organs that we want to treat, which is very ideal for treating different mitochondrial diseases. So the long-term goal of the lab is to first develop animal models and translate and also develop translatable gene therapies for mitochondrial diseases. And my lab is working on genes that are encoded in the nuclear DNA as well as mitochondrial DNA. Secondly, we want to further use those animal models and the experience and knowledge we learned from the previous gene therapy development to further enhance the precision of the gene therapy, meaning that we want to regulate how much AAV we want to give and how much protein that we want to express from this gene therapy for a safer and more effective gene therapy. So overall, an overview of the projects that are going on or that will be that will have in my lab is to develop gene therapy to restore the function of oxyphos system, that especially the ones that cause Leigh syndrome. First, as I mentioned that previously, we developed gene therapy for SIRF1. And also we're working on MT-ATP6, which is a subunit in the ATP synthase or complex 5. And also in the future, we are going to start a gene therapy development for the gene AFG3L2, which is a component of the matrix ATPase. And this gene plays a critical function to regulate the quality of the complex of the electron transport chain, meaning that it degrades the misfolded or unassembled complex subunits in the electron transport chain. So I'm going to first give a brief overview of what we did on SIRF1. And so SIRF1 is a gene that's encoded in the nuclear DNA, and the mutated SIRF1 causes a loss of function of the SIRF1 protein. So we think that we can develop a straightforward gene replacement therapy by so loss of SIRF1 then causes a complex 4 dysfunction. And so we think we can develop a straightforward gene replacement therapy by using AAV to deliver a functional copy of a SIRF1 gene, which then can produce a functional SIRF1 protein to restore the function of complex 4. And so for the first 2 years of my postdoc, that we developed this first version of gene therapy, and what we found that is by using the SIRF1 knockout mouse model, which is that previous mentioned that it's not a very good model. However, we were able to show that with the gene therapy, we were able to partially restore the complex 4 activity and decrease the lactate acidosis caused by endurance exercise in the with a long-term study. And also by treating the SIRF1 mice at an earlier age, we could not show the restoration of the complex 4 activity with this gene therapy design. And in the meantime, we tested this gene therapy in the wild-type mice that we found that it's safe. However, when we tested in the wild-type rats, we identified the cell degeneration and the mononuclear cell infiltrates in the heart and the DRG. So for DRG toxicity, it was widely reported in the gene therapy field, especially using AAV9 and administered through the intrathecal lumbar administration route. So that wasn't a big concern for us. But then with the heart, here I'm showing summary and example of the HE staining of what we found in the heart tissue. That on the left, we can see that at 28 days post-dosing, even with a low dose treatment, we saw degeneration and mononuclear cell infiltrates, as well as the mild fibrosis. And on the right, the two graphs are showing average severity grades, and we can see that there is no dose-dependent cytotoxicity caused by this gene therapy, although we saw a trend of resolution at 90 days post-dosing. And with the analysis on the genomic DNA and mRNA expression of the SIRF1, we think that in the DRG, it is mainly caused by the overtransduction of AAV9, which is reported widely in the field, but in the heart, it is caused by a SIRF1 transgene overexpression. So this is also not the first case where toxicity is reported in gene therapy. Here I'm using an example that was published for gene therapy developed for Friedreich ataxia, which express a frataxin gene. And as we can see in the summary figure on the left, when there's no expression, the level of iron sulfate is low, and when with a normal expression, we will see a normal iron sulfate cluster level. However, with this gene therapy, that the researchers reported that with due to a frataxin gene or FX and overexpression, they then also lead to a lower iron sulfate level, cluster levels. And on the right is an example of the data that published in the paper, where we can see that in this heart conditional knockout of frataxin mouse model, that when using AAV9 delivered frataxin expression gene therapy construct, the orange line is a low dose therapy, and we can see that it's extending the lifespan to about 15 weeks. But when you increase the dose of this gene therapy to 3-fold or 10-fold higher, then the lifespan of this mice is reduced. So together with our experience on SIRF1 gene therapy development, we think that when the gene therapy dose need to be tightly regulated for when you are talking about treating mitochondrial disease. So just showing a graph here to show you what I mean. When we talk about AAV getting transduced into 1 copy per cell, for a high expressor, so if the construct can exert high transgene expression, then we'll see increased mitochondrial health index, which in my case is a complex 4 activity. However, for a low expressor, so if you are using a construct to induce low transgene expression, then the health index would be low. And when you if we have more AAV transduced, more than 1 copy of AAV transduced per cell, then for the high expressor, then we will show a toxicity. But for low expressor, we will show an increased mitochondrial health index. So ideally, we would like to keep this therapeutic window in the top part of this curve. And so with all that in mind, then we decided to change the transgene expression construct design. And here, in the last 2 years, that we demonstrated that with a new construct, we were able to show partially restored complex 4 activity with an early treatment in the SIRF1 knockout mice. However, when you treated the mice later at a postnatal day 28, we weren't able to show a restoration because not enough cells were treated. And in the meantime, our lab developed a new SIRF1 knockout rat, and we were able to show that with the same time of treatment with and the same administration route, we were able to restore the grip stress deficits in the SIRF1 knockout rat. And this gene therapy was proved to be safe in the wild type rat as well, evaluated at 30 days post-dosing. So we are currently working towards trying to bring this gene therapy into clinical trial, and so continue into the effort in my lab that I am going to develop a similar approach for AEFG3L2 because the mutations in this gene also cause a loss of function. And we think that we can learn from what we did on SIRF1 and increase the precision and efficiency when we develop gene therapy for this gene. And we are also working on mitochondrial DNA encoded gene MTATP6. And so just a very brief summary on what we are doing on this gene, that we're taking advantage of the mitochondrial base editing technology to create a mouse model in editing both the germinal cells as well as the somatic cells, and also to provide a proof of concept using gene base editing technology to reverse the mutation in this mouse model. So I'm hoping that with all those efforts, we can we will not go to an end of journey, but over time, we will learn more and more about developing gene therapy for mitochondrial diseases, especially focusing on the restoring the function of OX4 system that cause Leigh syndrome. So with all that, I want to thank my previous mentor, Dr. Stephen Gray and Dr. Prashant Mishra at UT Southwestern, who brought me onto this journey and helped me learn all the technologies. And also my current department chair, Dr. Guangping Gao, and Dr. Beth McCormick, who gave me this opportunity to further develop the therapies to treat the kids with mitochondrial diseases, especially Leigh syndrome. And thank you, Cure Mito, for the continuing support and all my previous and current fundings. Thank you, Jessica.
Great. Thank you so much. It's good to see you.